Okay, great. Hi everyone. We're really excited to have Adam Lowrance, who will be telling us about ARC index and Turaev genus.
Okay, can everybody hear me okay? So it's wonderful to be able to give a talk in honor of Lou's 80th birthday. Like many talks, his work will play some role in what's going on here. Um, all of the things that I'm going to talk about today are joint with Alvaro de Valleviches, who's a PhD student at the University of Seville. He came to visit me last semester, and this is sort of what we worked on. I should say from the outset, this was inspired by a talk that I went to by Professor Jen, who's in the audience in Mobile, Alabama in 2023. He gave a talk on ARC index, and I've thought about ARC index a little bit in my career, but I've really thought about the Turaev genus a ton. And the pictures that he drew were very reminiscent of some work that I had done in the past, and I thought maybe we could connect these two things together. And Professor Jen's giving a talk in the first part of day 5, and it'll be on what I think is extensions of the things he talked about in 2023. So if you want to go see that, that would be great. So the plan for the talk, I don't really assume that you know what these things are. I'm going to tell you a bit about ARC index, a bit about the Turaev genus, and then we're not going to prove a theorem that connects them together. We're just going to give a conjecture, but we can prove that conjecture in many cases. And so I'll tell you about some of the cases in which we can prove the conjecture. And along the way, we'll get some computations of ARC index that didn't show up in the literature before. The one that I'm going to talk about in the talk today is adequate lengths, but in general, there's some other ones that will wind up in the paper. And all of this is work in progress. Okay, so let's do it. So we've heard ARC presentation a little bit in this conference, but just to remind everybody, you have an open book decomposition where you have the z-axis being the binding and you have finitely many pages, and then you just have a single simple arc in each one of those finitely many pages, and that's the link. Pictures are better than words. By the way, I've stolen pictures from many papers in this talk without attribution, but if the name's in one of the theorems, then I've probably taken your work from the pictures. So here you have the 5 different pages for the trefoil, and you can see it drawn in a more, you can see each one of them is a simple arc on the right-hand side. So that would be a 5-page embedding for the trefoil. Turns out that these things are equivalent to grid diagrams, and the proof is essentially this picture right here, right? You take the simple arcs and you draw them sort of rectilinearly like that, and then if you just imagine that you are viewing the left-hand picture a little bit from the side, you see the grid diagram version of this. And so the number of pages on the arc presentation for your diagram is going to be the number of rows or the number of columns in the grid diagram for the arc presentation. And Cromwell defined the arc index to be the minimum number of pages that one needs in an arc presentation. Okay, and that's going to be one of the invariants that we were going to talk about during this talk. So coming back to the trefoil, this picture, strictly speaking, just says that the arc index is 5 or less, but it turns out that this is a minimal representation. So you do get that the arc index of the trefoil is actually 5. Okay. So that's the definition of arc index, and then I'll switch gears and talk about the Turaev genus or the Turaev surface, and then we'll bring them together. So the Turaev surface is a link diagram. One way that you can construct it is you take the all A Kaufman state and the all B Kaufman state. You imagine that your link diagram is sitting, say, in the plane, and then you put your all A state above the plane, you put your all B state below the plane, and then you build a cobordism between them that looks like product cobordism away from the crossings, and at every crossing you just have a single saddle. And then if you do that, you get a surface with boundary. The boundary up above the plane corresponds to the all A state. The boundary below the plane corresponds to the all B state. and then you just cap those off with disks to get the Turaev surface. So again, pictures are somehow better than words. This is left-hand side is just a reminder of what the A and B smoothings look like. And then the right-hand side gives you a picture of a saddle that you place at each crossing. And maybe if you try to do this for a, I guess, what is this, like the 4-5 torus knot, or one diagram of the 4-5 torus knot, you have its all A state, you have its all B state, and then you have, it's not really the Turaev surface, it's the Turaev surface before you cap things off on the top and the bottom, but you can see what's going on with the picture a lot better there. Okay. That's how one builds the Turaev surface. You can compute the genus of this surface just by some data that you can pull off of the knot diagram, like the crossing number, the number of components in the all A state, the number of components in the all B state. That's not hard to see that formula. And then you do the thing that we often do with data that you can compute for a diagram. You minimize overall diagrams to get a non-invariant or a link invariant. And so if we do that for our example, this example has the crossing number being 15, there's 4 A circles and there's 5 B circles. And so the genus of that surface is 4. It turns out this is not minimal for the 4-5 torus knot, but that's what the genus of this surface is. A few little facts about the Turaev surface is that if you have the link L, it has an alternating projection onto any of its Turaev surfaces. So what we're seeing on the top is we're seeing I have scrolled too far, sorry. What we're seeing on the top is we're seeing 2 consecutive crossings. And this would be 2 consecutive crossings where if you looked at the projection to the sphere, they would go over. But what happens is that the surface twists between those 2 crossings with the way that it's constructed. And so it's the same picture on the top as it is in the middle, but it's just drawn from the top perspective. And there, when you're looking at the knot diagram from one side, you see the over, but you have a twist in the middle. And when you undo that twist, that's the bottom picture, you have an under-over. And so you get this alternating projection to the Turaev surface for any link diagram. And we'll say a little bit about history in a moment. And this theorem wasn't phrased this way. It wasn't even called a theorem in the original paper by Turaev, but its proof was in the paper by Turaev, so I attribute it to him. The Turaev genus of a link is 0 if and only if the link is alternating. So somehow the genus of this surface is giving you a measurement of how far away the link is from being an alternating link. And the proof is relatively straightforward if you think about what we just said. So if the link has Turaev genus 0, then we just talked about why it has an alternating projection to the Turaev surface. So the link has an alternating projection to a sphere. It's alternating. And then you have to think a little bit about it otherwise for the other direction. If you have an alternating diagram, then the all A state just traces out the components of the all A state are one of the checkerboard surfaces, and the components of the all B state is the other one. And so when you build this surface, you just get back the original projection sphere. And so that gives you the 2 directions of this theorem. So that's why I like to think of the Turaev genus of a link being some kind of measure of how far away the link is from being alternating. Okay, a little bit of history of the Turaev surface and the Turaev genus. So Turaev originally constructed the surface to give an alternate proof of one of Lew's theorems, and Mirasugi and Thistlethwaite as well. Turns out that you can get from this that the span of the Jones polynomial plus the Turaev genus is less than or equal to the crossing number. Used a different name. He called it, I think, atom genus. So Manturov studied this sort of thing, and he extended it to the class of virtual links, and also proved a relationship between this Turaev genus and the Kavanagh homology thickness. These papers, I believe, were originally in Russian, so I wasn't as familiar with them at the time. I came into this seeing some work, the other two papers here. So Shampanikar, Kaufman, and Stoltzfus did the Kavanagh homology lower bound on the thickness for Turaev genus, and then there's some work by Dasbach, Fuder, Kalfagiani, Lin, and Stoltzfus that kind of shows how you can lift the statement that the Tut polynomial of a graph evaluates to the Jones polynomial of an alternating link related to that graph. So I guess the graph is the Tate graph of one of the links. They showed how you can give an embedded graph version of that in 2008. So in my PhD thesis, I showed that knot floor homology thickness gives a lower bound on the Turaev genus. Something that's going to pop up later in the talk is that Cody Armand and myself, and independently Seung-Won Kim, showed that if you just want to look at the genus of the Turaev surface, so not minimizing, that all that really matters is what are the alternating tangles that are in the diagram and how are they connected together. The different alternating tangles, as long as they're connected together, the same would give you the same Turaev genus. We'll say more about that later. And then since 2010, there's a lot of other results that connect the Turaev genus to Kavanagh homology, knot floor homology, coefficients to the Jones polynomial, and so on. But those results don't play as big a role here, so I won't list them. Okay, so the main conjecture that I want to talk about today is this conjecture. The crossing number plus 2 minus the arc index is greater than or equal to twice the Turaev genus. So that's when I say how does our conjecture look for this family, that this is going to be the conjecture that I'm looking at. Okay. So the conjecture holds for alternating links. It holds for links whose Turaev genuses are 1. Turaev genus 1 links contain almost alternating links. They contain all the non-alternating pretzel links. They contain all the non-alternating Montesinos links. So that's a pretty big class. We also show it for adequate links. You can show it for torus knots, closures of +3 braids. And maybe the first thing I did was just go to knot info and look if this conjecture holds for all the knots in which these invariants are computed in knot info, and it does. Alternating links in Turaev genus 1 links, we barely have to prove anything. We just notice some facts that other people have proved about these classes and put them into the conjecture, and things pop out. It's a little bit to do with adequate links. The adequate links and the torus knots and the closures of +3 braids, we had to work a little harder. Not terribly hard. So what I'm going to tell you along the way is kind of the story, and then when we get to adequate links, we can talk about their arc index as well. Okay, so now we're going to shift gears again and come back to arc index and try to think about how we can relate these two ideas that we've talked about so far. So if you look at an arc presentation as the one that we originally had, and you just look at it from the top, then you get a picture like this. The binding is right there in the center. The numbers here, this would completely determine the arc presentation by telling you the relative heights at which you enter and exit that page, the simple arc. But for me, I just really want to look at the top-down picture for now. And then I want to imagine kind of what would happen, or what's one thing that could happen if we stay viewing it from this angle, but then we perturb the picture slightly. We perturb the knot slightly. And what could happen near the binding is something called a stacked tangle. All right, so if we perturb the binding just a little bit, then and take a regular neighborhood, you will have these arcs that pass through that are at different heights. Right? And so if you stare at this, you get a you can imagine that we would take the picture on the bottom there, and we could shrink that down to a point, and it would become the binding of the arc presentation. So what I would like to do, or what I would like to think about, is can we take an arbitrary diagram, just any diagram of a link, and somehow recognize a chunk of that diagram so that it becomes a stacked tangle that could eventually become the binding of an arc presentation. And this is not my work, right? So Jen and Lee gave a procedure to do this, and we'll draw some pictures of it in a moment. Jen and Lee's procedure was actually just a different combinatorial way of doing something that Bay and Park did previously. So they get some of the credit here when we go to the theorems. So the idea is you start with a diagram on the left, and you're going to think of that diagram as a graph, right? Where the vertices are the crosses. And you're going to build a spanning tree of that graph, and that spanning tree is going to have to satisfy certain properties. And you're going to build it iteratively. So I didn't write down the properties. I'll try to tell you what they are, but they're sort of technical. The point is that one can do this. So you start by picking the first edge, 1, and then you pick subsequent edges. The first rule is that everywhere in the process you have to have a tree, right? So you stay connected, and if you end up with a spanning tree, well, you never had any cycles along the way, so you don't have to worry about that. But you pick edge 1, you pick edge 2, you pick edge 3, and so on. The next rule is that at everywhere other than the last step, the edge directly across from the one that we're picking can't have both of its endpoints in the tree already. All right, so this is just some technical condition. So for instance, if we have the graph 1, 2, 3, and we're at that step, the rule is that when I pick 3, this edge, the edge directly across from 3, can't have both of its endpoints already be in the subgraph 1, 2, 3. So there's ways that one can do this. And then there's some other third condition, which is slightly more technical, and maybe I won't say, but you can read about it in Jen and Park's paper. I'm sorry, Jen and Lee's paper. Because this is combinatorial equivalent to something that Bay and Park did, you can always build such spanning trees. So they prove this. And what ends up happening is that once you have a spanning tree like this, you can then take a regular neighborhood of that spanning tree. So imagine the green highlighted part is thickened up just slightly more. The boundary of that regular neighborhood is then a topological circle in the plane. And that's what we see on the right-hand side. So the green shaded pieces on the left just become the green arcs on the right. A little subtle here is that the blue numbers mean something different on the right and on the left. So the blue numbers on the left just mean how we built the spanning tree. Turns out that the blue numbers that when you do this process, you always get this stacked tangle behavior. And the blue numbers on the right are telling you the height of the arcs in the stacked tangle. And so there's a procedure for doing this, and it's a pretty simple procedure. You just draw the first arc in and give it some arbitrary height. And then you draw the arcs subsequently. And if your arc goes under something, then you write it as, the smallest, the one smaller than the smallest number that you've used already for a height. And if your arc goes over things, you label it one higher than the highest number you've used already. Okay, so big picture wise, start with an arbitrary diagram, do some spanning tree stuff, and then turn it into a regular circle, and you get this stacked tangle behavior. But what's going on the exterior is a little more complicated. So maybe I'll skip back for just a minute. Now, if we imagine perturbing from this top-down view and thinking about what happens not near the binding, but away from the binding, if we just perturb a little bit, then you're going to get arcs on the side that look like this, the arcs that aren't nested. All right. So it turns out that nested arcs can be a bit of a problem, but that we can denest many of them. And so what happens is the arcs are labeled by the heights that they enter and exit the stacked tangle. And as long as the arc that you want to denest sits outside of the range, so A and B are the arcs of the interior one, and C and something else are the arcs of the other one. As long as C sits above A and B, then you can kind of swing the arc beside it and denest them. But if it's interleaved in some way, then you can't do that. And the strategy is to break the arc that involved C into two different arcs, which would then increase the arc presentation, the number of arcs in the arc presentation. Okay, but the beauty of the theorem of Bay and Park, and it's reimagined this way by Jin and Lee, is that the only arc that you end up having to break is the arc that deals with the very last edge that you added into the spanning tree. And so that shows up in this picture as this arc that goes from here, 1215 to 215, and then here, 2 to 15. And so if you think about this, you built a spanning tree. The spanning tree has C-1 edges in it. The diagram has 2 C edges in it. So there are C+1 edges that aren't in the spanning tree over here. The arcs on the side, you had to take one of them and split it into 2. So that gets C+2 arcs that are on the exterior. And the arcs that are nested, you can denest because they fit into this top category here, this top picture here. And so that's a kind of different combinatorics, but the same argument and spirit for what Bay and Park proved here, which says that the arc index is less than the crossing number plus 2. So for any diagram, you can build this crossing number plus 2 arc presentation. Okay. So now we can say a few things about alternating lengths, and in particular, we can prove our conjecture for alternating lengths. So here's where Lou's work pops up, and also work of Morton, who spoke just a moment ago. The Kaufman polynomial, Morton and Beltrami proved that the Kaufman polynomial gives a lower bound on the arc index. And the span of the V span of the Kaufman polynomial is known for alternating knots. It's the crossing number. And so when you put together the theorem of Bay and Morton and this theorem of Beltrami, Bay and Park and Beltrami and Morton, you get the corollary that says that the arc index for a prime alternating link is crossing number plus 2. And then, well, the Turaev genus of alternating links is 0, and then the left-hand side of our conjecture is also 0, so you get equality there. Okay. Okay, let's go back to this picture that we showed before. There are certain arcs that are really nice. So, right, let's look at this portion of the diagram. You can see my cursor, right, as it moves? Okay, so this portion of the diagram, this is a stacked tangle. This is at height 12. You have a little arc that goes outside of the tangle that goes from between height 12 and height 11. And you have another arc that comes into the tangle at height 11. And so what you can do, because these are adjacent heights, is you can just push this arc inside of the stacked tangle. And then you have to choose, it was height 12 and height 11, but now that can be given a single height, either height 11 or height 12, or any number you want between 13 and 14. I'm sorry, between 10 and 13. I can't think about numbers. but that allows you to decrease the number of arcs in the arc presentation. And so anytime you have these interior arcs that are adjacent heights in your stacked tangle, you can push them inside of the arc presentation, inside of this version of the arc presentation to get fewer arcs. And what Jin and Park proved is that if you have so I think Stoimanov made a similar comment in his talk. The two parks that I've talked about so far are different parks. So the Bayan Park and Jenin Park, I think, are different here. If you have a non-alternating diagram, you can always cancel at least two of these arcs. And so you get that the arc index is less than or equal to the crossing number. This follows up some work by Beltrami, where she proved that were always less than or equal to C+1. And then Jen and Park improved it to say non-alternating knots always make you less than or equal to the crossing number for the arc index. And so that gives us the conjecture for Turaev genus 1, right? Earlier, we proved that you're Turaev genus 0 if and only if you were alternating. So Turaev genus 1 means non-alternating. Therefore, the arc index is less than the crossing number, which gives you the first part of the centered equation at the bottom. And that equals twice the Turaev genus for Turaev genus 1. Okay, so like I said, the alternating and Turaev genus 1 examples, we just sort of noticed that this conjecture holds by theorems that other people had already proved. Okay, so now comes the part where I saw the talk in Mobile that made me start thinking about this. There's a series of papers. There's, I think Jen and Lee are authors on all of them, and Stoimanov is authors on several of them. And then there's many other collaborators involved that are at their heart trying to figure out what are the minimal grid diagrams or the minimal arc presentations and building an atlas of these sorts of things for different grid numbers or different arc indices. But the strategy that they propose is they give a way to choose how to do these spanning trees to make sure that the edges that you're going to cancel correspond to these non-alternating edges. So they give we sort of noticed by example that you could push these edges in here, right? Well, they give a procedure that very frequently allows one to be in the situation that we see on the screen where you can push these in. Okay, so this piqued my interest, and it piqued my interest because, like I said, when we did the Turaev genus section, Cody, Armand, and I, and independently Seung-Won Kim, had some work that dealt with Turaev genus and sort of the alternating tangle decomposition of the diagram. So let's say a word or two about this alternating tangle decomposition. This is originally, at least to my knowledge, due to Thistlethwaite. So you start with a link diagram. You take every non-alternating edge, so every edge that goes over, or under, you put 2 dots on it, and then you connect them like the picture. So you connect each dot to its nearest neighbor, but you don't connect the dots that lie on the same edges. And if you do this in every single non-alternating edge and for every single face that contains a non-alternating edge, then these arcs become closed curves. And on one side of the arc, you have alternating tangles, maybe tangles with quotations, because sometimes you can get non-disk regions. And in between them, you get non-alternating edges connecting them. So for instance, here's an example. The non-alternating edges are exactly the ones that intersect the red curves, and you just connect them up this way. So this is 4 different alternating tangles connected up and by these non-alternating edges. And what Cody and myself and Seung-Won proved was that if you have two diagrams such that their alternating tangle decomposition is isomorphic, and you build the Turaev surfaces of these diagrams, then they have the same genus. And so in the example that we had, what that means is that if I take this picture and take any or all of the tangles that I have sitting there and replace them with any alternating tangle, it has to satisfy some very slight conditions, but any alternating tangle that meets the boundary in 4 points, and you construct the genus of the Turaev surface of such a thing, it will have the same genus. And in this case, the genus of the Turaev surface is 1. So somehow, on the one hand, we're using these non-alternating edges to drive the arc index down, but on the other hand, we have these non-alternating edges that have something to do with driving the Turaev surface, the genus of the Turaev surface up. And so that's the strategy that I sort of propose for attacking this. You start with the alternating decomposition. Maybe you want to start with the fewest crossings because you want to minimize crossing number as well. You have its alternating decomposition. That allows us to compute the genus of the Turaev surface. And then you use the methods that Jen Lee and Stoimanov and others say to pick this spanning tree to try to find as low of an upper bound of the arc index as possible. It turns out this works pretty well, but it doesn't work all the time. So I'm not going to get into a huge number of details for positive 3 braids, closures of positive 3 braids, but that's a nice infinite family where this approach works. If you've dealt with 3 braids before, you know when you start to classify them, they break up into many cases, and it's just you sort of slog through the cases and show that this procedure works. And Alvaro, my collaborator, has done great work on figuring out how to do this procedure for positive 3 braids and driving their arc index down as low as possible. And some work that I did, I don't know, 10 years ago or so, computed the Turaev genus, or maybe off by 1 the Turaev genus for closed 3 braids using a Kavanagh homology lower bounds. And so when you put the 2 things together, you get it for the positive 3 braids. So just to put a bow on this example that we've been looking at the entire time, this is an example where this sort of strategy works, right? The 2 edges that we have arrows on here are the ones that correspond to 8, 9, and 11, 12, and you can push those in. That tells you that the arc index is, well, I guess in this case at most 13. It turns out to actually be 13, and so crossing number plus 2 minus arc index is exactly 2, and the Turaev genus of this knot is 1. So that equals twice the Turaev genus. Interestingly enough, an example where this strategy, not just where we can't make it work, but where we've proven that it will not work for this diagram, is right here. So this is a sort of complicated alternating decomposition. Turns out it's Turaev genus 2. And if it's Turaev genus 2, then you need to cancel 4 of the edges. You need 4 of those special little arcs that you can push in. And if you work through the combinatorics of all the possible spanning trees that you can build, there's a lot of symmetry in this picture, so that gives us, makes the argument a little bit easier. You're never going to be able to get 4 arcs that one can push in. It turns out that this example is adequate. We'll say more about what an adequate link is, and we can actually show that the conjecture holds for adequate links, but we won't be able to do it using the method that we've talked about so far. Okay. So I think now is the time that I want to switch gears a little bit and talk about the other way that we're going to think about this that gives us the adequate result. 6 minutes left. Okay. So as we already saw, there's a relationship between arc presentations and grid diagrams. if you take a grid diagram and you kind of just turn it on its side by rotating it 45 degrees, you get a Legendrian front diagram. If you rotate it the other way, then all the crossings are the wrong way. So you get a Legendrian front diagram for the mirror. If you've studied arc index, then this is something that's probably familiar to you. You have to, if you turn it on its side, it has corners that are both north-south and east-west, and the Legendrian front diagrams, you need to smooth the north-south corners into smooth curves. The Thurston-Benneken number, you can of the Legendrian link, you can compute straight from the diagram. It's the rive of the diagram minus the number of right-hand cusps. And so this picture is it's a positive knot. There's 6 crossings, so its rive is 6. C of F is what I'm calling the right cusp. There's 5 of them, and so the Thurston-Benneken number for this Legendrian link is 1. And then the maximum Thurston-Benneken number of a link is the maximum of a classical link, is the maximum of all the Legendrian representatives. All right, so this relates to arc index. I think I attributed this to Matsuda. Stoimanov might have attributed it somewhere else, so I'm not sure if I'm right. But the arc index has a lower bound of the negative of the maximum Thurston-Benneken number of a link minus the maximum Thurston-Benneken number of its mirror. And the proof is straightforward, right? You have the lower bound quantity. That quantity is certainly less than or equal to take any Legendrian front representation and compute those. The Thurston-Benneken number for that Legendrian front is the rive minus the number of right cusp with a negative sign, and then similarly for the mirror. But now you have the rive of a link diagram minus the rive of its mirror. And so those two terms cancel, and you're just left with the number of right cusp when you turn it one direction, plus the number of right cusp when you turn it the other direction, which is exactly the number of corners that you need to achieve to get the grid number for that diagram. So that's the arc index. What I'm not going to explain is a much harder theorem to prove, is that inequality is actually an equality. So this is due to Denikov and Prasilov. And so if you know the Thurston-Benneken number of the link and of its mirror image, the maximum Thurston-Benneken number of a link and its mirror image, then you know its arc index. Okay, maybe in the interest of time, I'll skip through this. Okay, so a link is adequate if no two arcs in the A resolution of any crossing is adequate, if no two arcs in the A resolution of any crossing lie on the same component. Similarly have B adequate. And what Kalman managed to do was give you the Thurston-Benneken, maximum Thurston-Benneken number for adequate. It builds on work of Lenny. And well, I'm not going to prove it, but the picture that happens is here. You start with the all A state, say, and then Kalman gives a procedure to take the all A state and turn each one of the components into this I shape with one left-hand cusp in each and one right-hand cusp. And then you can, and the arcs are remembering where the crossings were. And then you can take the arcs where the crossings were and replace them with crossings. And the diagram on the left and the diagram on the right are planar isotopic to one another. And the two slides that I skipped basically say that there's something about this diagram that ensures that that a Kaufman polynomial lower bound for the maximal Thurston-Benneken number is tight. All right. And so that gives us that we can compute the maximal Thurston-Benneken number for any A adequate link. You can do the similar thing for the mirror. And so when you put this result together with Prasilov and Denikov's result, you get the arc index of adequateness. So it turns out that there was a conjecture for this already. I won't go into what the 2 row of D term is. It's something that you could compute from the the checkerboard graphs of the arc diagrams. But when you put these two things together, you just get that the arc index of an adequate link is the sum of the number of components in the all A state and the all B state. And then we can prove that this is in fact equivalent to the original conjecture, this term 2 rho of D. And again, the proof is just putting together the Kalman result and the Denikov and Presilov result. So there we go. And that tells us that our result holds for adequate. So the inequality that the conjecture for adequate is in fact equality. And so the example that we showed earlier that we couldn't get using the top-down stack tangle approach, we can figure out that our conjecture holds using this other approach inspired by Kalman. Okay, so roughly speaking, maybe I'll skip over torus knots. We can also prove it for torus knots. The arc index was already known for torus knots, and we can find the right diagrams that minimize Turaev genus low enough to show the conjecture for torus knots. And so this is all work in progress. Some of this we know more than others. So we do have a few other infinite families that I didn't talk about today that we can prove the conjecture for. We also can use this idea that we've talked about the last few minutes by Kalman and Denikov and Presilov to find a few other infinite families where I think weren't known before, but we can know what their arc index is. And then something that I'm thinking about is, since both of the methods we used don't really, there are certain examples that we're pretty sure they're going to fail on or that we know they're going to fail on. Maybe we could weaken the conjecture some, and instead of putting a 2 there, we could put some number that's between 0 and 2 as a coefficient of the Turaev genus, and then maybe be able to prove that. So I'm putting some thought into if we could add that to our work. Okay, that's all I have to say. Happy birthday, Lou.
Great. Thanks for the talk, Adam. So it looks like there's one question in the chat. Yeah.
So in your conjecture, weaken GTL into toroidally alternating. Is that possible? I should know the answer to this.